Hey folks, welcome to tonight's stream. We're going to be showing a version of... Oh, hey, my titles aren't working right. Let's try this one. Is this one working right? No, none of them are working right. But we're doing a stream tonight of one of the best presentations from PacSec, which is Ilja VanSprundel and Joseph Tartaro from IOActive, who had the tour de force epic dump of looks at pretty much all the bootloaders and found problems with most of them. It was a presentation that's well worth reviewing because pretty much every computer has to boot. So without further ado, let's cut some fancy graphics and begin that presentation. See you on the other side.
Okay, so continuing on in our exploration of the first thing all our computers do, please a big hand for Ilja's been presenting here at PacSec. This is his third time. I call him one of the most dangerous men on the planet. And Joseph is his first time here presenting at PacSec. Please a big hand for these two. I've been given a little bit of a sneak preview. You know, Andrea was talking about the problems with file system parsing, and we had some questions about file system and U-boot. And I think these guys are going to show you exactly how that works.
Hello, thank you for coming. This is boot2root, auditing bootloaders by example. So I am Joseph Tartaro. I'm an Associate Principal Security Consultant at IOActive.
Hi, I'm Ilja VanSprundel. I work for Joe. I'm the Director of Penetration Testing at IOActive.
So basically the audience that we expect for this presentation are people like embedded systems engineers, security folks that deal with low-level devices and secure boot stuff, or just generally curious people that want to learn a little bit about this stuff and dive into it. And hopefully some of this will inspire you to go further and have it no longer be this secret black box. And so the quick agenda, we're going to discuss quote-unquote bootloaders, why it's a concern, and some of the common bootloaders. We looked at the open source projects we audited and their interesting supported features. We're going to cover the attack surface because there's appears to be a lot of attack surface that people don't realize, and then examples of bugs in the attack surface, and then our conclusions. So, quote-unquote bootloaders, we're using kind of like a wide interpretation. We're basically more or less talking about various things in your boot chain that could be compromised. And if you've never really toyed with this stuff, you can kind of think of it like user land and kernel space. You're writing code in user land and you try to reach into kernel space to do things. Similar here, you're going to have code running in bootloader land, and we'll talk to kind of like a secure world or reference BIOS calls or UV calls, things along those lines. You'll have things like system management mode and stuff that you're reaching into, which is the prime target. And hopefully that kind of makes sense to chain it all together. So why? If you were here for Andrea's talk, you should understand it a little bit, but basically it's a key foundation, security foundation for your chain of trust. If you find a bug and you can get code execution earlier in the chain, you can basically compromise everything past that. Because all the security is ensured by what happens before it. So another concern is a lot of device engineers basically are poor at hardening their devices and limiting the attack surface. And what we mean by that are people who build a device and they include a network stack, but they don't actually use it. Like all you're doing is giving an attacker a lot of attack surface. There's no reason for you to have that, so why have it? And also engineers tend to underestimate reverse engineering. They they kind of think that it's a black box and nobody's going to see it, and they kind of leave it that way, but it's a concern that people should be aware of. And a little story behind how this presentation even happened was Ilja and I were actually on a train to a baseball game, and we were looking at a device that had U-boot, and pulled out our phone and started looking at some code, and quickly became shocked because we stumbled into like 13 bugs like on the train ride, and went, oh my god, we should probably look at this and a bunch of other ones. And in about 20 minutes we put together an agenda for a presentation and basically spawned this on the train ride. So really quick to give credit where credit's due. This is a list of people who basically inspired us in this realm, and these are all people that you should kind of look up and check out some of the work they've done, because they've done some really cool things, and nothing that we're doing is necessarily new. We're not the first to look at this stuff, and we're not the last. So Secure Boot, Andreas covered a lot of this stuff. Basically you have a train of trust and a whole bunch of different stages, things like measured boot, trusted boot, and then you'll have things like a TPM involvement, and then something like trust zone, and then a operating system that interacts with these things. So basically the goal is to break it earlier on so you can affect everything else, but that's the entire window that we're looking at. And where do you see these things? Everywhere. Basically every device, servers, desktops, your phones, your game consoles, your TV, everything has this stuff, and there's always going to be a dependency on it, so it really, really does matter. So, common bootloaders, we basically limited ourselves to publicly available open source projects. All of these are used in the real world. It's realistic, but every device is heavily customized, so you might run into a device that has a ton of custom hardware drivers, for example, and different things, so we're clearly not going to see that in the base code. So when you decide to go audit a device on your own, that's going to be all like fresh attack surface for you to look at. But in the base code, this is a list of what we covered: U-boot, core boot, grub, CBIOS, Cafe, which is Broadcom's, iPixie, and then Tiana Core. So, and I apologize, this is a little dry. We're basically going to go over each one and the interesting features and why we're looking at them. But U-boot, as you can see, it's extremely common. I think earlier we said 1 billion devices basically have U-boot, and it basically supports a wide range of boards and CPUs, and that's why it's so popular. And you'll see that there's a ton of, or massive configuration file where people can tweak everything about this, and a lot of people like to leave it relatively default. And it has a pretty powerful shell, so if you ever looked at UFI shell, it has a very similar one with people integrating different features. You'll find issues like basic command injections and stuff, but there's a little bit of attack surface there and some fun stuff to poke at, and then lots and lots of device drivers. It supports a network stack with a bunch of different protocols, some different file systems, and a lot of different methods of loading your file systems through all these different devices, and some of them are very archaic and probably worth looking into, like disk on chip and stuff, and yeah, it's extremely popular. So core boot, this one is targeted at modern operating systems. It does not support legacy BIOS calls. So you'll find in core boot code, they'll never have a network stack, for example. If you need a network stack, you need to boot into something, they just expect you to boot into iPixie. Or if you need to do legacy BIOS calls, they expect you to boot CBIOS, for example. They're not actually taking on those features, so they did a good job at kind of limiting the attack surface. These are used in Chromebooks, and the more interesting parts come from Google, obviously. And one interesting thing to note about this is Coreboot actually has a system management mode. And in Grub, I'm sure everyone here is familiar with Grub. Its primary concern is multi-boot spec. So it handles a whole slew of file systems. So this is kind of your interesting attack surface, all these different file system parsers here. And there are also UV signed versions of Grub. And the reason that matters is because if you can go ahead and take a secure boot chain that involves UV and load a vulnerable version of Grub that is signed and trigger a bug in it, now you're good to go. And CBIOS. So this is kind of like the legacy BIOS calls that we talked about. For example, Coreboot will load this up. It gets loaded by a ton of different bootloaders that basically want to support those features. It supports TPM, which is a Trusted Platform module, and it's also the compatibility support module for UP and OVMF. And then Cafe. This is Broadcom's bootloader. You're going to see this in all sorts of networking devices and TVs, stuff like that. It is open source and has a network stack that's interesting attack surface. And iPixie, basically same thing with the network attack surface, but you'll notice that iPixie supports way more protocols than any other bootloader you'll look at. So that's the more interesting aspect. And another example is there are UP signed versions of this as well. And then ultimately Tiana Core, which is EDK2 and UP. It's needs no introduction. Everybody has looked at this. I spent a ton of research over the last 15 years. A lot of interesting work. It's by far the most scrutinized and attacked, so it's definitely the most mature out of all of them. But it's also because it's probably the most used. And you'll also find that other implementations are based on Tiana Core. Things like if you're looking at an Android device that has a Qualcomm Android bootloader or extended bootloader, that's all built on top of Tiana Core. And then there's some things related to bootloaders. So you'll have stuff like the Trusted OS. Those are kind of like the secure world components we were talking about, where it's a good attack surface because you're calling from, imagine like user land into kernel land. You're in this normal land trying to call into these secure realms. So if you get code execution in there, you basically won. And then the host OS, it can have some interaction with the bootloader. It can do things like modify the NVRAM for environment variables, things along those lines. So this is just a slide for you guys to reference later, take a picture or something, but it's just a quick link to source code and instructions for building these projects. So if you want to build a quick audit environment and focus some of this stuff, it's just a quick way to get started. Wait for him to finish. Cool. So let's get into the attack surface. So a lot of the common attack surface that we saw across the board is we broke it up to NVRAM, which was the area that we saw people storing things like the environment variables, which are user controlled, files and file system parsing, network stacks, various buses, and system management mode, as well as DMA and hardware attacks. So quickly getting into NVRAM, like I said, environment variables, these things can be modified from the OS runtime or physically modified at a hardware level. It's generally stored on a separate piece of hardware, but I think in some environments it's like on disk and stuff. But you kind of have your standard concerns. These are user controlled, attacker controlled, and a lot of people will just kind of assume that it's not. So if you look at some of the source for these projects, you'll see these common calls like environment git environment, etc. And if you wanted to go and audit the source code a little bit, every single time you see this call reaching into an environment variable, you just simply look, how are they handling the data? And if they're not handling it in a secure manner, you have a bug there. So, quick explanation or a quick example is inside UBoot, you can see the red square that was just highlighted. It does an environment git call for boot p VCI. And this environment variable is then checked if it exists. And if it does exist, it passes it to this put VCI function. And once it gets past the put VCI, it simply does a stir length check, or a stir length on it, and then passes it to memcopy. There's no sort of validation on if it can fit inside the buffer or not. And you have the basic stack smash there. And this is kind of what we were talking about when we were on the train and we went, oh God. So I saw examples like this, and we should really kind of look at this. Another example, environment get to a host name. Same exact thing, just does stir length and passes it straight to a buffer without checking. And as you can see, it's consistent. We have a 128 byte buffer here, and same exact thing. It's just a stir copy straight into that buffer. And keep in mind that I believe the default size for environment variables is 512 bytes. But some configuration files will go even higher, like hex 2000 bytes, hex 8000 bytes. So, yeah. Yeah, so you can see there's a lot of examples here, a lot of stuff to look at, and it just keeps happening everywhere. So to give you a quick look at how trivial this stuff is, if you wanted to start poking at this stuff, is just real quick. It's nothing more than booting up UBoot, and in this case, the code we pointed out happens when it does like DHCP, for example. So we just set up these two environment variables by home, called DHCP, and it crashes. And quickly look, and you can see we control a handful of registers and whatnot. So if you've never looked at this stuff and it is kind of black box to you, but you think it would be interesting, you can kind of see there's like a low barrier of entry, similar to what Andrea said in this last presentation. Some of the quality of code and things you're running into are, things that you'd see 15, 20 years ago. So it'd be good practice for you to basically start poking up.
Yeah, so if you were paying attention to the questions when Andreas was talking, there was a small discussion about file systems, and I was thinking, oh, that's interesting, because about half an hour from now I'm going to be talking about this, and sure enough, here I am. As Andrea correctly pointed out, one of the massive attack surfaces in a secure boot environment is your file system, because the thing needs to boot. In order to boot, it needs to read files and data, it needs to get that from a device, and it has a file system, and so you need to parse the file system and get to the files. The first thing you do is you have to mount your file system somehow. That includes, reading a bunch of blocks and things like that, and store things around and keep things in memory and sort of parsing certain things. Depending on which environment you're in and which file system you're using, and your file system may or may not be signed or integrity protected. Usually, depending on your environment, some are, some aren't. But usually you can get something going where it isn't signed, or you have to mount up to a certain point before you can do a bunch of verification. So often your file system has lots and lots and lots of attack surface. A simple example, for example, is a FAT file system on a USB device. Even though FAT is one of the one of the less complex file systems and sort of well-known, well-tested, well-worn-out file systems. So there's usually less bugs in your FAT file system. There's usually more bugs in other file systems. So because of that, obviously, this is a private attack surface. Obviously, once you mount your file system, you have to actually get to your files. And again, as was pointed out earlier, some files will be integrity protected and they might be encrypted. But depending on your boot environment and in what situation, some files may not be encrypted or integrity protected. And so parsing of those files obviously is also an interesting attack surface, and I would say prime example, prime attack surface. And those file parsers should absolutely be considered attack surface. So I'll be showing some examples of some X2 in Grub for the file system stuff. But in terms of files, I mean, this could be anything, right? Where if you're reading a driver from a file system, or a binary, or a partition table, or a capsule update, or a bitmap splash image. And the splash images are usually never signed because you want to be able to customize those kind of things. And I'll demo some of that as well, or what I like to show about. So I hope you can read this, but basically this is a Grub when it's parsing X2 symlinks. It basically does reads a symlink, and this right here, this reads. It takes this size that it read from the file system, and it does +1. So the size is really big. It's 0xFFFFFF +1. That means 0, and so grub malloc basically allows an alloc at 0. It gives you a valid pointer to a piece of memory that can hold 0 bytes. So that works. And then once you get the valid pointer back, it calls a grub2 read file, and it gives it, here's the pointer, here's that really big length, which is 4 gigs. And what's really, really nice about this file read API is that it goes, oh, well, the file is only 1,000 bytes. Instead of copying 4 gigs, we'll just only copy 1,000 bytes into this buffer that can only hold 0 bytes. And so this is your very standard trivial buffer overflow where you can basically, even though the size is 4 gigs, you can actually control the actual amount that gets copied, and you control all of the bytes that get copied into it. So this obviously allows for a compromise of a signed grub. Another example, it would be so that's the splash bitmaster example. This is an example in Tartaro and Ilja that was very, very recently fixed and was found by multiple parties independently. I can't comment on some of the parties, but some of those people may be around here. So this basically, the idea is that if you have a very simple 4 or 8-bit bitmap, the idea is that every bitmap gets a palette, and so if you have a 4-bit bitmap, your palette can have up to 16 colors. And so they have this array of 16 bytes in which they copy the palette, but you can basically create a corrupted 4-bit bitmap where your palette is bigger than 16 bytes, and they just copy the entire palette into this 16-byte buffer. And then the same thing happens for the 8-bit bitmaps. So this was in Ilja for a long time, and it's fixed maybe 2 months ago, 3 months ago, something like that, right? So up to recently, this got you a Ilja break. So that's it, sort of a quick overview of files and file systems. And this is just a tip of the iceberg. There are many, many, many more. But since we're not going to stop with file systems, let's move on. Let's now that we've done the environment stuff and we've looked at the file systems, let's look at the remote attack surface of bootloaders. It's very common for a bunch of bootloaders to have a network stack for some reason. Usually, it'll have your entire TCP/IP stack. It'll support, Ethernet and IP and TCP and UDP and ICMP and all those low-level protocols. And then, of course, they're pretty useless if you're not using actual services. So usually, on top of that, they'll do things like loop P and DHCP and DNS and ISCSI and NFS and IPsec as corporate environments, and HTTP, HTTPS, and THCP and so forth. And you'll see these things re-implemented in a whole bunch of different bootloaders. So common observations in general is when you're looking at low-level TCP/IP stuff, essentially at a very high level, all these protocols are basically TLVs, right? They're type length value. And as we all know, when you start fuzzing stuff, when you see TLV, denial of services, so if you're looking at TLV, then denial of services are incredibly common. You'll see things like endless loops and out-of-bound reads and things like that. This has plagued every network stack known to man, and that includes all the network stacks in a secure boot chain. On top of that, you'll see things like DNS and DHCP, and there's these sort of very, very old, very well-known DNS and DHCP games where you can start spoofing stuff. And the idea is, generally, you try to fix these things by introducing some randomness in IDs. This is a well-known concept that's been around for a long time. All the bootloaders re-implement this code from the 1980s, and they all make the same classic mistakes. On top of that, obviously, these things are parsing a bunch of blobs and binary data that comes over the network. There are memory corruption bugs. And then last but not least, you'll see info leaks, something like heartbeat or ether lead or something like that. That shows up with some regularity. So let's take a look at U-Boot's DNS. This is really nice because the DNS ID is 1. It is always 1 for every DNS packet, which means doing spoofing and intercepting is extremely trivial because the DNS ID is always 1. Looking at Cafe's DHCP reply parser, for example, it has this 128 byte stack buffer, and then it goes and reads a uint8, which can go from 0 to 255, and then it'll take that length field and copy from the network up to 255 bytes into the chunk buffer, which is 128. So this is your absolute classic stack smash. This stuff is not compiled with Stack Protector, so this is like 90s style pre-auth remote stack smash. This is used like skewed roots over at this point. Another Cafe example. This is TFP. It's the same thing, right? In this case, it's a 512 byte buffer that's in the structure, and then they copy into it, and the amount of data they copy into it, which is the max that fits in one of these eBuff structures, which this doesn't show here, but it's capped by the Ethernet MPU, which is about 1500. So again, trivial memory corruption bug right here. Here's another one. This is in their ICP ping handler, where it has this, you send the ping and it's waiting for a response, and it has this loop, and it has a timeout where if after a certain amount of time I don't receive the right packet, I bail out. And so every time it gets it back in the loop, it says, looks at the magic ID and goes, oh, is this the packet I'm looking for? Oh no, free, and then wait for the next one, wait for the next one. There's a weird quarter case where it sees a packet and then goes, oh, not the one I'm doing, it frees, but it doesn't set the packet to null. And then once it goes back into the while loop, it goes, oh, timed out. And then at the end of the while loop, it frees the thing again. So this is your classic double free and use after free. This takes some effort to exploit and trigger, but it's very, very classic. And then another because why not Cafe? Why not IP? Why? Another interesting one. This is the Cafe, the standard IP input parser, and it looks at your the length inside of your inside your IP header that sort of describes your content, and it doesn't validate at all. It just trusts it, and then it starts setting its buffers based on that length. So if you make that length really small, it triggers an initial underflow, and so that will lead to things like thinking there's 4 gigs of data that arrived, even though your buffer only has like 20 bytes in it, or it can have things like where you make it really big, and then that can lead to out-of-bound reads and out-of-bound writes. But enough of these fancy stuff. And there's plenty more bugs where that come from it. As I said, again, this is just the tip of the iceberg. You start with these bootloaders, and U-Boot is not the exception. U-Boot is more like the rule. Most other bootloaders are of a similar kind of code quality. But let's be done with XUIP, but let's still, what's the next step in sort of the boot attack surface? So some bootloaders actually support Wi-Fi and 802.11. When it comes to this stuff, there's sort of, because they have to talk to the radio, and there's sort of 2 kinds of radios, right? You have the radio that has a lot of very thick firmware that basically takes all the frames and it does a lot of pre-validation in the radio, and then it'll, over SDIO or USB or whatever, talks to your boot chain and says, here's the packets. And then there's the other kind of radio, which is basically just it's like pass through. It takes frames from the air and doesn't do anything. It just passes it to your secure boot. For the purposes of sort of this discussion, we are basically assuming that second kind of radio, where there's no validation on the radio. As to whether or not that happens or not, very much depends upon which radio you're using. The other thing is that 802.11 is not as common yet in bootloaders. This sort of gives you the philosophical between, is this sort of accidental attack surface reduction or purposeful attack surface reduction? My guess is accidental, whereas people haven't implemented the features yet, but at some point they might. And then sort of the optimist in me likes to hope that, well, maybe it's purposeful. Maybe they considered it 11 and they discarded it. Unfortunately, reality has shown time and time again that usually it's the first and not the latter. But one of the bootloaders that does support 22.11 is IPXE, and this is one of the decryption routines where if you give it a zero-sized piece of data to decrypt, it basically does length divided by 8. 0 divided by 8 is 0. It does -1, and AAS unwrap does in memory transformations, so decrypt in memory. Because you give it a length to -1, it'll do in-memory decryption of 4 bits of data, which obviously triggers memory corruption. Now this is kind of, it'll trigger a crash, but trying to exploit this is would be a pain in the ass. However, this one is your classic SSID parser bug, where, yeah, that's the one, the 90s called. So you get this IE that comes over the air, and you start parsing it, and you go, oh yeah, well here's the IE element, and then you take the IE element length, and you copy it into an SSID, which is 32 bytes, even though your length can be up to 255, and then this is a straight up stack smash. This is straight up, this is even before your connect memory, so it's straight up SSID into a stack buffer with no stack cookies, smashes straight into, and you can overwrite a safe instruction code. And then, so those are some of the bugs we found, and then I went out and looked for some recent stuff that other people looked at. And so this is a recent CV that came out a few months ago from Qualcomm in some Android stuff. And then here's another one that was found by the little Android team in some of their WLAN stuff. So this is just to show that the bugs we found are unique. There are plenty of these things go around, and they're in your boot chain. So now we've done the TCP stuff and the high-level services and the 8.11. So what's left? Okay, well, Bluetooth. And first of all, well, why Bluetooth? Well, it turns out when you're talking Bluetooth for boot chains, it's because there are some boot environments where you want to have HID devices, so you may want to have a keyboard or a mouse, and obviously they can use Bluetooth, and so some boot environments will support Bluetooth. Now the good news is, in terms of accidental or purposeful attack surface reduction, most boot environments do not, and that's great because at least you don't have to boot an attack surface. We did see one earlier, a boot environment earlier this year that had a really big Bluetooth stack with numerous Bluetooth bugs. And based on that sort of, just if you look at the protocol high level, so the low level L2 cap type stuff in Bluetooth, which is sort of the L2 stuff where all the other stuff are layered on top, is basically it can use fragmentation. And the idea is the lengths are all UN16s, which means once everything sort of gets reassembled, you can have a frame that is up to about 65,000 bytes. And so that basically opens you up to a whole bunch of these 90s style fragmentation games. And sure enough, we didn't learn less than TCP, we did it in Bluetooth as well. Tons and tons of fragmentation show up. You have really large fragments or really short fragments, something that doesn't fragment right, or something that doesn't, like in the middle, things go bad, and they go bad really fast. If you're lucky, it's a download service. If you're not lucky, it'll be memory corruption. As I said, this doesn't show up in much boot environments. So I was desperately looking for an example in open source. I couldn't find it because they don't support it. Not a single one we look at, unfortunately. I wish I could show you the ones we did have, but those are covered by non-disclosure agreements. So basically, instead, we looked at some recently fixed bugs in a bunch of Android stuff. So this is a Qualcomm driver, and this is remotely triggerable, where basically, if you're doing an authentication at the same time you disconnect, there's this weird remote race condition where if you do the disconnect before the authentication then happens, the device is already deleted, but the function pointer on it is still called. So now you have a function pointer, something that no longer exists. And this can lead to remote code execution, basically. This was found by Qualcomm, and this was, I think, in August Android update. Yeah. And then here's another one. This was another one. This was released to a remote pointer. But my point is, even though we couldn't find a bootloader that had boot stuff, there definitely is Bluetooth stuff in a bunch of like Android type devices, and they absolutely have security bugs. So now we've covered N, and we've done the files and the file system and network stuff. So then Joe and I were like, well, okay, what's the next attack surface that's interesting in secure boot? And we were both like, well, obviously USB. And the reason why we say USB is because there are a handful of scenarios that are very common in the boot environment where you use USB. So obviously HID device, right? Mouse and keyboard. Things like fastboot, things like recovery mode, and stuff like I want to boot this image off the USB stick, right? So those are the 4 common scenarios, and most boot chains, even secure boot chains, will support at least one of these 4, if not multiple. And in order to do that, you have to have a USB stack. And we audited quite a few USB stacks over the last year, and I can tell you, nobody does it right. These are things that easily break. So USB is this thing which is like it's almost packet protocol based. It looks a lot like it, and it's these things where once you plug the thing in, and the host sort of gets notification of it and goes, oh, okay, well, I need information about who you are. And it says, basically, send me this descriptor, or this descriptor, or this descriptor, which tells me about what kind of device you are. And so basically, your host OS, or in this case, your boot chain, has to parse all of these descriptors that come in from your USB device. And it turns out that parsing descriptors isn't always very easy, and it's usually not done with a lot of care. The 2 sort of generally types of bugs that we've seen here are just straight up overflows, where you have static arrays of like, well, the spec says you can have up to 8 interfaces. No way a device would ever send you a descriptor that has 9 interfaces, even though it's just an extra bit, So straight up overflows, very common. The other one, which is kind of sort of unique to USB, or sort of is sort of a case of, is you have all of these double fetches. Because of the way descriptors work is, so descriptors are this thing where you have a small, depending on which descriptor, 2 or 4 byte header, and then it has a bunch of content. Now, because they're variable length content, your host never knows exactly how big they are, because the device gets to set how big it is. So the way it works is the host goes to the device and says, give me the first 4 bytes of your descriptor, which I know is your header. And then the device goes to the host and says, here's the first 4 bytes. And the first 4 bytes contain a 2 byte length field in there, like W total length or something like that. And then the host does an alloc based on that. And then it goes back to the device and says, okay, give me that same descriptor, but now give me the header and all that, all the length after it, based on the length you gave me. And so it rereads that header, puts it in the buffer, and then hands that back off to a caller. The problem is, if between the first and the second fetch, the length in the descriptor changes, and you don't catch it, you'll have a descriptor that has a length field that has not, or was validated the first time but not the second time, and because of double fetch, it overwrites the first one, and so you end up parsing something with a length field that's not validated. This is extremely common. I've seen every single USB stack break on this. You can write a test case for this and you'll see stuff blow up instantly. So again, let's go look at Grub. Grub obviously has handles USB, and it goes and gets a descriptor, and then the descriptor basically has a configuration count, and it basically has a for loop that loops from 0 up to configuration count, and it adds into this device configuration index I, and then it puts stuff into it. Now that is something that is statically defined as 8 elements, but I can make a config count that's 9 or 10 up to 255 from the device, and this will trigger memory corruption. And of course, we're not done yet. There's also a number of interfaces, which is also statically defined in Grub, and there's no bound check on this. So if you make a number of interfaces up to 255 or something, there'll be a second memory corruption bug right there. So that's a 2 for 1. Django core, so this is Eufy. Recently also had some USB fixes that were applied. This also happened 2 or 3 months ago. But the idea was basically, it was this similar thing where it does the first fetch and then it takes two bytes, and then it does the second fetch with that link and it copies into it. And in this case, this link is a UIN8, so it's up to 256. And so they didn't add a bound check here, but what they did is they looked at the caller and they changed the buffer size. So that hub desk is commented out, and it's now a UIN8 array of up to 256, and then they cast a pointer to it. And that sort of implicitly fixes this bug. Okay, and then so CBIOS talking about these double fetches, CBIOS has this classic one where this one goes to USB and says, "Hey, go get me a config descriptor." And then the config descriptor has this W-total length field, and then it goes and it allocs it and goes, "Oh, go get me this config descriptor again." And now the config W-total length can be different from the CFG W-total length. And if there's a mismatch, that means whoever starts handling that, because the config gets returned, and so the W-total length can now no longer correctly describes the actual buffer length. And that the users of this function can trigger out-of-bound reads and out-of-bound writes. So just to show that, this is a bug we didn't find. But this is, for example, USB as an attack surface is how the Nintendo Switch got jailbroken last year. So this is very early on in the recovery mode in the boot ROM of Nintendo Switch. There was basically you could get it to go through this recovery mode, and then you could plug in a USB device and basically give it this very particular get status request. And what it would do is it would take a link that you gave it, a UIN16, and then it would take that UIN16 and would copy into this quote-unquote DMA buffer. And without any length validation, the DMA buffer was considerably shorter than 64K, and so you could use this to reliably smash memory. And in fact, this was used to root the Nintendo Switch. There we go. Yes. Okay. So we've so once with the USB, you sort of ask the question and go, oh well, what about the other buses? Well, that's obviously attack surface too. You could certainly say anything that's not DMA can easily be attack surface from a secure boot point of view. And so one example is that flash is often connected over SPI, and depending on what you're doing, your flash may not be trusted, or parts of your flash may not be trusted, and basically anything connected over the SPI shouldn't be trusted. But there's other buses and things like that. So for example, your TPM is often connected over LPC or SPI, and unless you're using two-spec mutual lot, the data that comes in over your LPC or SPI bus from TPM shouldn't be trusted. And there was a good presentation by the guys from NCC, I think 2 years ago, about all of these sort of TPM parser bugs. Your bootloaders are no different. Linux breaks and Windows breaks and Eufy breaks, but also CBIOS breaks, where it takes a length field, but it actually tries to validate it, but it only looks at the upper bound and not the lower bound, and it's sort of a variable length data structure. And so if you give it a length that's really, really smaller than the header, it will basically take that length and subtract the header length, so you end up with a really, really large value, which is now in your size. That's underflow, something really big. And then it turns out, if you look at CBIOS, malloc high actually has an internal integer overflow. So now you underfloat something really big, and then you give that really big to malloc high, which basically gives you back a pointer of zero size length. And then that length is used, your underflow really big values used to copy into that very small buffer. The malloc high, the implementation is because it's pretty complicated, but like you can take my word for it that it has an overflow in there. But I will quickly run over this. But this part isn't very important. But the code is kind of hard to follow. But basically, malloc high calls malloc, which calls malloc padlock, and then malloc padlock calls malloc new, and malloc new has this thing where they have this linked list of sort of chunks of data that describe something that is partially allocated, it has some free space, and it has this, begin pointer, and end pointer, and sort of where the stuff that's allocated, and then the rest of it is unallocated. And then it does some math based on the size you give it with a line down. Anyway, I don't really have the time to run through this, but feel free to take a picture of it or look at this later. There's absolutely a bug in here. It's in that red box. I'll leave this. I'll leave this as exercise. Whoever, by the time I'm done, can explain the bug to me, I'll give you $100. Okay. Was it? You want me to go back? Was it not enough time?
And just real quick, just to get emphasis on that region, one thing that we kind of noticed is that designers and developers, if it's something on this weird bus and on a device or a component that an end user should never actually be using a standard use case, they kind of just inherently trust it, which is an issue. They don't actually consider it potentially dangerous. That's just a common thing that we've seen across the board.
Okay, so the next sort of attack surface is things like system management mode and trust zone. So in x86, there's SMM. And if you don't know what that is, there have been, there's a decade and a half worth of security research on this. Some of it presented at PacSec and PacSec. Really, really interesting stuff. I'm not going to go too deep into these specifics, but the point I'm trying to make is implementing SMM and implementing it right is very, very hard. Intel has tried to do this for a decade and a half. And it's this arms race where somebody finds a break, they improve it, somebody else finds another break, they improve it. This is a game that's been going on for a decade and a half. They've gotten a pretty good grasp on things. On occasion, there's still some breaks, usually in the third-party stuff, but Intel at this point has got a pretty good grasp on it. And so if you look at the SMM implementation in UFI and Tiago Core, like, you're pretty good. I mean, not saying it's without its flaws, but it's pretty decent. Now, if you're going to do an x86 bootloader, you're going to do SMM, and you're going to re-implement the stuff from scratch, you are in deep trouble, because this stuff is really hard to get right. You're definitely going to screw it up the first 10 times, which is what coreboot does. So coreboot installs this SMM handler, and to their credit, they go, oh, you know what, before we look at the data you give us, we range check, and then, oops. The range check basically says to do. It just says return OK. So you can give it any pointer, and then you can basically get it to read and write to SMM over memory on your behalf, and that absolutely works. Because we're running out of time, and Andrea did such a great job to talk about trust, so I'm just going to skip over this. And we're running out of time, so I'm going to skip over the host stuff as well. Let me talk about the last piece I want to talk about, which is DMA, which is memory access. And again, Andrea brought this up as well. But basically, if you are really serious about having a secure boot, you can't just have unfettered DMA access, even though that is the way stuff was originally designed. You've got to do something about it. A lot of the bootloaders, especially when you look at the open source stuff, haven't really gotten a handle on this yet. If you're making a bootloader and you're at least thinking about DMA attacks, you are at the present time ahead of the curve. That's not to say some people haven't, absolutely. I mean, UFI now has support for this stuff. If you look at CSMA, it has supports for this. There was a talk a few weeks ago about the design of the Xbox security system, where they talk in depth about sort of the DMA controller that does memory encryption integrity stuff. So some people have designed around this, and one of the points that was sort of made in the Xbox presentation was, up until recently, sort of off-the-shelf components didn't really give you a way to sort of manage DMA where you could have it be a trust boundary. That is starting to change, in part because of virtualization, but also because people are asking for this as a security feature. And so people came up with this thing called an IOActive unit, which is basically, a memory management unit that says, you as host, as the thing that runs on CPU, you go and program it, and you say, okay, by default nobody gets access, DRAM, and then you say, oh, that's device A can access this piece of memory, and then your device B, well, device B can access this piece of memory. And if you program it right and you do everything correctly, then you can now restrict DMA access and sort of create that DMA as a trust boundary, which is great because all of a sudden you no longer have to trust devices that do DMA. Now, with that, of course, comes new attack surface, because now all of your DMA parsers have to be secure, and because nobody rewrites these things from scratch, it's always a version of a version of a version that somebody wrote 15 years ago. Your DMA parser is going to be full of holes because it was never a trust boundary to begin with. So if you're doing IMU and you're doing it right and you're programming it correctly, go back and look at your DMA code because it's going to be very broken and it'll have tons of bugs. Secondly, because you now basically have this model where it's not mapped to devices by default and you sort of expose it to them, you have to not just expose them, but you have to clear your memory before you expose it to a device. Because otherwise devices can now go look at physical pages that you give them. If you don't clear it, you'll be exposing things that are left lingering from before, and that could contain things like crypto keys or something like that. And then sort of outside the scope of this presentation, but sort of in the back of my mind, I've been thinking about this for months, and I haven't seen presentations on this yet, but I guarantee you there's bugs there, and it's hopefully something I get to play with in the next months or maybe years, or somebody else will do a presentation about this, which is sort of attacks on the actual IMUs. I strongly suspect there's bugs there. My guess is you'll find side channels and logic bugs and hardware flotation bugs. I just haven't had the time yet, but it sounds, especially now that we're at the point where DMA is a trust boundary, these IMUs seem a lot of fun to play with. Yeah, in terms of bugs, here's one that's currently and because so most of the other bootloaders that I've talked about don't support a lot of IMU stuff, but Tiana Core, being fairly mature compared to the others, does have support for IMU to their credit. But they have this configuration thing where you can configure it two ways. You can enable bit 0 and bit 1, and bit 0 basically says enable IMU during boot. And then bit 1 says enable IMU when transfer control to OS, which means bit 0 doesn't do that. So what this means is, and you'll see that by default it says 1, which means they only set bit 0, which means they only enable the IMU during boot. Once they transfer control to the host OS, they turn off the IMU programming, which means now the host OS can re-enable it. But in between those two, you have this window where all your devices now get the DMA into anything they want to. This is a known problem in UFI at the present time. The Intel people are very much aware of it. They are trying to fix this, but the problem is this requires you to design a protocol with the host OS where you agree on how you program this thing and how you do the correct handover, which at the present time has not been standardized, and because it hasn't been standardized yet, it can't be in the open source implementation, and because everything else is based on the open source implementation, that means everything that at the present time uses Tiana Core is absolutely vulnerable to this. But they are working on it in the future. This is going to get fixed with a protocol that doesn't exist yet. Cool. This is
yeah, and just to quickly cover some hardware, this stuff is kind of out of the scope of the whole presentation, but we thought it would be silly not to at least mention it to you guys. And what we mean by hardware attacks, we mean things like glitching, side channel, and silicon attacks. And this is really only relevant to devices that are in the hands, physical hands of the attacker, things like game consoles, stuff like that. And so real quick, glitching. This is stuff like introducing fault injections. There's a really cool blog post there that you guys should read. It's from a group called Failed Overflow, which hacks a lot of game consoles. And they recently did a glitching attack against the PS4 Syscon chip. And the idea was basically it would go into an infinite loop. Like, if I remember correctly, no, I don't have debug mode enabled, and it would just sit this infinite loop, and then they would just glitch it, and it would pop out of the loop, and then debug is enabled, and they can dump the code and everything. You'll also see other similar types of issues, like lowering the voltage of a microprocessor or something, where you'll see a standard implementation would be a device that will let you program it and then set a secure flag, and now that the device is programmed, it could be wiped, but it can't be read. So you can do things like tell the device to wipe, but then drop the voltage a little bit, like right after. And every once in a while, you'll stumble into a chip where you can basically tell it to wipe and then drop the voltage, and it will wipe the security bits and then die. You reboot it, and then now you can read out the secure code. And so just things to be aware of, to look out for. Things like side channel timing discrepancies, power consumption discrepancies. These things will leak secrets, and you see people attacking hardware all the time in this manner and extracting secrets. So, and then chipsec. This is more against like silicon attacks. Things like decapping, actually, making a hole in the enclosure of the chip so you can see the silicon die, using things like a focus ion beam or a scanning electron microscope. Obviously, attacks like this would be for a very sophisticated attacker, but every once in a while, there's people who have equipment to do it. And this was like a common thing where you saw people, extracting keys out of the satellite dish cards, so they can hack satellite dish stuff. And basically something that people should be aware of, like I said, where people kind of underestimate reverse engineering. The boot ROM will probably be extracted in one of these manners, and so somebody's going to start reverse engineering your boot ROM. So you should might as well audit it and do it right, because eventually somebody's going to get it. Kind of our conclusions. Like we said, this covers the tip of the iceberg. The point of this presentation was not to, show a bunch of bugs and laugh and flex. It was more to kind of express to you guys the amount of attack surface that's actually there. From the conversations that we had with people, it just seems like people aren't really aware of how much actual attack surface there is. And from the quality of code and the bugs that we stumbled into with relatively low effort, it's clear that people really aren't looking at them. And one thing that's kind of silly is you end up in NBA hell really quick if you try to look at proprietary bootloaders and boot ROMs, and it's just something that you're just never really going to get access to it unless you sign your soul away, and it's a total nightmare. But yeah, so obviously some of the advice we have for people who are designing these things, clearly you should limit your attack surface and on both your boot environment and your host operating system. Maybe you can use Andreas project from the presentation before us, and turn off features you don't need. There's so many times we're looking at a device and we go, oh, that's funny, you're using U-boot and you have a full network stack, but they don't need a network stack, or they will mount a certain type of file system that they never care about, never plan on parsing, but why is the code there? And then also another concern is we see embedded Linux with more drivers and attack surface than our OS or our desktop at home, and it's just kind of crazy to see that in like a tiny little embedded device. So it's just kind of a clean up what's there, guys. And then another main thing is the lack of exploit mitigations. We pretty much saw like no stack protectors, no dep, maybe ASLR in SNM only, but not outside of it. Issues like that, and clearly since Tiana Core is the most mature one, it's ahead of the game. We put a little GitHub link where somebody went through and kind of demonstrated a lot of these exploit mitigations that are going to eventually end up in Tiana Core.
A lot of it's recently been ported, right?
Oh, has it? Okay, yeah. So a lot of it has been. But yeah, it's something that definitely the other developers need to start taking note of and implementing as well. So a little call to action. Basically, if it wasn't obvious, more people should be reviewing this stuff, and we hope that the long list of attack surface and the examples and bugs that we showed will kind of inspire some of you to start looking at it as well. Maybe you can go out and hunt for some CVs or something, or get some practice looking at this black box that you never thought of looking at before. And people doing basic things like fuzzing various interfaces. Basically everything we found you would have trivially found with some basic basic fuzzing and bit flipping, really, really low effort stuff, and it's pretty clear that some periodic reviews are necessary. So, and yeah, that's it.
I don't think I've ever seen so many bootload bugs dumped in one short hour in my life. It's like we're screwed. Anybody have questions? I'm sure there's got to be some questions. Yep.
So I have a question with respect to the IOActive that you mentioned. So with respect to one would expect a secure bootloader to have a lockdown configuration, right?
You would, yes.
Right.
Now that's the difference between you expected and it actually being there.
Right, so that's the question. Like, among those that you've looked at, how often did that happen? That they would say, you know, if you're supposed to boot on the file system, you can't just modify this configuration and boot.
Yeah, that's a good question. It varies wildly, very wildly. It usually depends upon, I mean, if you look at commercial devices, look, at the end of the day, it comes down to budget, right? If you're making a device that you secure boot, depends how much money you're going to throw around on your security team. If you're going to spend money on your security team, you're going to have really insecure designs. And usually what happens is you start off that way, and then they get owned really badly, and then they said, oh, we must spend some money and hire good people and have a security team. And then, 2, 3, 4, 5 years later, you build up a good security team, and they start, like putting screws to it, and looking at your design, your configuration, and things get better and better and better. There's some we've looked at that over the last 2 or 3 years have gotten really good. I was looking at one bootloader about a month and change ago, and they got to the point where their bootloader, they sort of made their own sort of Pico kernel and has a user land that has these tasks that do these things that are deprivileged tasks just in your bootloader that then just turn everything on and then put the OS. So that to get to that level that's pretty impressive. Some people do that, but it's usually an evolution. You don't start that way. It's just you get beaten into submission and end up having to do that.
And yeah, I think the common trend that we see in a lot of devices is people just trying to get it out as soon as possible, and that is the default configuration. The moment they get it kind of loading, they go, cool, we're done, and they move forward with it. And basically 100% of the time it's pointing out very clear issues as to we're just going to stop auditing this code because you're not even supposed to be using it, or at least we recommend that you shouldn't even be using it. So as for what we've seen, I don't know, but at least for in the presentation, we're kind of limited to open source projects and default stuff. So as all the bugs that we showed, likelihood, severity, who knows? It was just more of showing examples of each component.
More questions? Going once, going twice. Please, a giant hand for these very dangerous gentlemen. I put back one question. Is there anyone left standing?
There's one we haven't touched yet, so I would say there's a boot ROM we haven't touched yet because they wouldn't let us play with it. So that one is still standing because we haven't been able to get to it.
So you haven't found any all of the ones you looked at, none of them have survived so far?
Not one survived.
We're screwed. Thanks.
Well, folks, that was our stream for this week. Next week, we should be announcing a whole bunch of the panels for PacSec, which will be again November 1st to 4th. And also, we'll start announcing the courses. We have, I think, 8 to 10 courses that we're going to be putting on at PacSec. And we'll hopefully soon have a schedule for kind of a marketing bazaar. We're going to give some 30-minute samples of courses for folks in a free seminar, so you can see which training is right for you and kind of do a little bit of visual shopping for trainings. Anyway, lots of announcements, and we'll be streaming out another interesting and informative talk next time. So hopefully we'll see you all next Wednesday. See ya.